count 0. Right? So yeah.
Okay.
So actually, let me take my restroom break now. And then...
Yes.
All right.
Blame the victim.
Your name, your last name, I never.
Johnston-Halperin.
Halperin.
Halperin?
Halperin.
Yeah, that's fine.
Okay.
Don't worry about it.
Is that true?
The office that
By law.
by a few minutes.
Sorry?
Depending on the.
Yeah. No, I'm familiar with the phenomenon. We've met somewhere before. That's right.
What I wish you to say is work with Michael.
Yeah. It's just the correlation problem when you're traveling. Is this on? I think this is on.
It's just for recording.
Oh, it's just going straight to the... Oh, okay. Oh, good. Well, I think I just ruined the video. Oh, well. So you're going to APS this year?
Yes.
Good. So hopefully I'll see you there. How long are you staying?
The whole week. It's spring break and our talks are on Friday. That's why
Yeah, I'll have a student talk on Friday, and then I'm giving a talk on Wednesday, so I'm flying out Tuesday. I find the older I get, the less time I can survive at the APS meeting before my head explodes.
Are you also traveling next week?
No, I'll head back. I have to go to this sorting meeting in Chicago, and then I'm home on Saturday. I'll be home for a week, and then going to. I was traveling basically all of February now. So
You are not teaching this semester, right?
no.
That's good.
Yeah, no, that would not be possible with all this.
Promise me you're not going to use the word galaxy.
I've heard that from more than one person. I was trying to come up with something sufficiently clever to put on my my cover slide, but I couldn't really come up with anything. How do I turn this on?
Oh, do you have a USB?
Oh no, I don't want to. I just want the laser.
Oh, okay. Then turn this on.
Oh, that's the on.
Yes, it's on.
Okay, great. I'll probably just wave at the screen, but just in case. Have the pointer.
Well, welcome to this first condensed matter seminar after a month of astronomy's Colloquium. I'm glad to introduce today's speaker, Ezekiel Johnston-Halperin. He's a professor at the Ohio State University. He got his bachelor's degree in 1996 from Case Western Reserve University and PhD in 2003 from University of California, Santa Barbara, working with David Ashland. If you know the name, then you know that he's working on Spintronics. Okay. Then he moved to Caltech for a postdoc, working with James Keith. The well-known work was high-density memories based on silicon nanowires. That's when I first heard his talk, and he was giving a talk at UC Riverside. Then he joined the university, the Ohio State University in 2006 as an assistant professor, and then became associate professor in 2012. Zeke has been working on a lot of systems with a focus, I would say, on magnetisms and spin phenomena. Since he started his group in Ohio State, he has made a lot of progress, significant progress on spin injection and spin transport in semiconductors, but especially recently with using organic boromagnets for spintronic applications. So that's what he's going to talk about today, and hopefully use by the new opportunities in organic spintronics.
Thank you, Sarah, for that very nice introduction, and thank you all for the invitation to come and the opportunity to come talk. I'd also like to quickly say this is one of the great pleasures of the job, to see people who I met as talented young graduate students burning up the lab at Riverside, now being very successful here at Utah. So good hiring decisions. And I promise there will be no exoplanets, no quasars, no galaxies, unfortunately no gravity waves. I wish I could talk about gravity waves, but nothing like that. I would say actually that I spent a lot of time going back and forth on how to put this talk together, because As Sarah mentioned, organic spintronics is a focus of maybe a third to a half of our work. And normally when I give this talk, especially as a colloquium, I spend a fair amount of time introducing spintronics, introducing organics. But I feel like that's a little bit overkill here at Utah because you guys have so much good work here. So I went back and forth, but in the end I decided on the side of pedantry for a colloquium. So for the many, many experts in the audience, please forgive me if I go a little slowly at first. I'll just try and sweep everybody up and at least maybe give my flavor of some of the results in the field and why my group in particular is interested in some of this physics. So I want to start by thanking the collaborators and the people who did the work. The people in italics at the top are current and former members of my research group, whose work you'll be hearing about today. This entire area of research started basically because of very fortuitous happenstance that I landed at Ohio State, where Art Epstein was very active in this area. He's since retired, but a lot of you'll see his name on a lot of the papers. It was really essential for getting us started in this area. And then for a lot of the microwave measurements, learning about FMR was a collaboration with Chris Hamill and his students. And some of the more recent unpublished work that hopefully I'll have time to get to been done in collaboration with Georg Schmidt at the University of Halle. So broadly speaking, I would say the opportunity here for organic spintronics is applying sort of freshman level English literature skills, organics and spintronics. And the advantages of organic materials are manifold and I think pretty well known. They're commercial successes and very powerful. The advantage of spintronics are a little more complicated and somewhat in the eye of the beholder. One thing I would like to emphasize here is, especially listening to research talks, you hear a lot about the next thing spintronics can do for you. And a lot of it can sound pretty exotic, but I do want to take a moment to emphasize that spintronics is already a multi-billion-dollar industry. This is how GMR read heads work in hard drives all over the place, and in fact, the first spin torque RAM, magnetic RAM memories are on sale from Everspin, which have applications in space and other radiation-hard environments. So there are real opportunities as well as sort of science fiction sounding ideas about spintronics. But at a very basic level, the thing I'd just like to point out is that inorganic materials, inorganic electronic systems benefit greatly by the ability to integrate multiple degrees of freedom. Not just charge in transistors, but also optical functionality and magnetic functionality. And of those big three, we've got two in organics so far. And integrating the third in, I think, has some significant promise. So, with apologies for my excessively cute language here, I want to give two different views of the motivation for spintronics. And so this is sort of the kind of thing you find in the introductory paragraph of papers and grant proposals, and is very exciting. And it talks about fundamental limits, and spin is an alternate state variable for information technology applications. So in terms of quantum applications, quantum information, spin is a very interesting variable because the time scales for this coherence are extremely long compared to most other variables, most other degrees of freedom, up to milliseconds if you get the right system. Another interesting fundamental limitation or opportunity, depending on how you think of it, is that if you want to think about the fundamental energy required to do an operation on a spin, it's dramatically lower than the minimum energy for a charge-based operation, simply because capacitive coupling to the environment is always going to be there at some level. So it sets a low threshold or a high threshold for the lowest energy for charge. And in particular, periodically over the years, you hear more and less excitement about this potential for even zero dissipation operation, which is sort of a perpetual motion machine that you probably should not trust too much. More practical and more near term, though, is the idea of spin as an additional state variable, to use the language of computing. So rather than fully replacing charge, we can augment charge. One of the more famous examples of this is the idea of a spin-based transistor, which is not a charge-free device, but incorporating, at least in one incarnation, non-volatility into a charge-based transistor at the transistor rather than having a remote memory. There's also other manipulations that are possible. And broadly speaking, it increases this phase space of multifunctional operation. So we can transduce spin between many different degrees of freedom, sort of multiferroics being one example that people may be familiar here. But basically the philosophy here is start with charge functionality and then add this degree of freedom. So trying to make this one step more concrete, going from words to at least pictures, and this is physics I'm sure everyone's familiar with, but I just want to go through it with a particular slant to make my point. So I'm sure everyone's heard of a spin valve, but fundamentally this is a spin resistor, right? And this is the first big hit for Spintronics. As I mentioned, it's all over data storage. But it was sort of explained and conceived at some level really as a spin analog of a charge device. It's a spin-sensitive resistor, such that if you have two magnetic layers that are oriented the same way, charge flows relatively easily between them. If they're oppositely oriented, you have a higher chance of reflection, and there's sort of well-established formalism for understanding this in terms of the density of states and other. There's also other more interesting sort of interface effects and other things that can come on, that can come in. But this is a pretty general idea, and this is, say, Spintronics in the 80s and 90s. As the 90s moved to the 2000s, the focus moved from passive electronics, which is basically a resistor, to active electronics, and this idea of a spin transistor that I mentioned before. And so this is really easy to do in PowerPoint, harder to do in real life. When I was at Santa Barbara, this was the kind of thing I was trying to start to do, at least, as a graduate student with various levels of success. Basically, the idea is, rather than a stacked device, you go to a lateral device. It behaves in many ways the same way as for the vertical device, with charge flow, which depends on the density of states of your electrodes. And basically, you create a spin polarization by exploiting the correlations and the exchange interaction in your ferromagnetic electrode. You inject that polarization into your channel. That spin diffuses, or you can even apply a bias if you want, and then you extract that spin polarization at your analysis electrode, which is just the time reversal of injection. So this much is just a topological transformation, which doesn't add any new functionality. The idea of the spin transistor, though, is that now you've opened up the channel for doing more sophisticated operations and controlling the spin. So, for example, in the famous Dada DOS proposal, they propose to use a gate electrode to extrinsically modulate spin-orbit coupling and manipulate the spin as it moves between these two electrodes. So far, I've been very sort of application-oriented in my description of the field, but I want to point out that these three sort of key components of a functional spintronic device lead naturally to very interesting fundamental questions about materials and physical processes. And I just sort of list some of them here. There are many more to think about. This has basically been the trajectory of inorganic spintronics, which is to add functionality to charge-based electronics and sort of implicitly to mimic the development pathway of charge of these very successful charge-based strategies. So coming back to this integration, this opportunity to cross over into organics, there are a number of ways this can happen. A lot of people have shown interesting work with spin valves, exactly analogs of what I just showed. Our work in this area was to, rather than focus on the channel, to focus on the injector And this is the work that started in collaboration with Art Epstein, using this organic material, vanadium TCNE, which I'll talk about in a lot more depth a little later in the talk. But this is using a measurement paradigm from charge-based electronics again, or excuse me, inorganic spintronics, known as a spin LED. So basically you inject current into a light-emitting diode. You inject electrons from the top, holes from the bottom. In that red quantum well region, they recombine and emit light. This is done in a 3-5 semiconductor so that the optical selection rules of that recombination process convert any residual spin polarization in that current into an optical polarization. So our idea was, well, VTC-NE is a good magnet, but we've never really done any of this spintronics type work with it before. Maybe we can measure or the spin polarization, or even demonstrate that you can extract spin polarization from VTC-NE by using it as a magnetic electrode in this device and then looking at the polarization of the light that comes out. So there's a lot that I'm not talking about to sort of do the control measurements and all this, but basically if you look at this red data here showing the polarization of the heavy hole luminescence line, it mimics very closely the green data, which is the hard axis magnetization of the VTC-NE. So this is sort of one demonstration from our group, and not that this is unique, that you can start to develop organic spintronics on the same pathway as inorganic spintronics. I will point out the last bullet here that, at least for our work, this is technically challenging. For example, with the VTC-NE, this is what a real device looks like. This little dash is the bar, and you can see it lives in this can because it doesn't like air. So we have to keep it in an argon atmosphere as we go from the glove box to the measurement apparatus. This is possible. You know, one of the hallmarks of physics is doing hard experiments, and this this satisfies. But even though this was a successful experiment, and you know we got some interesting results, just sort of to give you the timeline at this point, wasn't clear where we wanted to go forward with this. Because this is challenging and it wasn't, you know, these numbers are not large, that were going to require a lot of optimization to get to a useful device, and inorganic spintronics works. So really what was our new direction going to be? And this also, you know, independent of the science, but as I'm sure many of you can appreciate, of some significant importance, this is also when Art Epstein started to ramp down his efforts, and so we had to decide, you know, are we going to continue with this and take over all aspects of the collaboration, or should we find something else to work on? And almost exactly at the same time, there was a big change happening in the world of inorganic spintronics. And so that's part of the motivation that I want to talk about here. And in fact, actually, one thing I wanted to point out was the publication date on this paper. Right, so this is 2011, and so in the discussion I just gave, I played a little bit of a trick on the audience. So feel free to throw fruits or cookies or copies of, you know, old astronomy presentations. The motivation I just gave you was my standard colloquium motivation up until about this time. And this, in my opinion, typified the motivation for the whole field of spintronics. But then around that same time in 2011, a phenomenon was rediscovered. Say many, you know, there's always, once you know what's happening, you look back through the literature, you realize this thing could have been maybe seen previously, but it's this idea of dynamic generation of pure spin currents. And so here's a schematic from this sort of very well-known paper by A.G. Saito's group, where you have a ferromagnet immediately adjacent to a non-magnetic material. I think this paper is permalloy and platinum. And when the ferromagnet's static, sort of nothing interesting happens. But when you apply microwaves and excite ferromagnetic resonance, you can drive a spin current across this interface. And then the role of the platinum here is through the magic of the inverse spin Hall effect, which I'm not going to talk about again, so I won't really explain, but I'll just say generates a transverse voltage that you can monitor, and as the DC applied field sweeps through the ferromagnetic resonance, you see this spin current turn on. So the key issue here is pure spin currents. And coming back, maybe I'll jump ahead and then jump back. Coming back to my slide, sort of the trick I played was I implied that this is purely hypothetical and this is what we can actually do. In my opinion, the big deal about this emergence of dynamically pumped spin currents, both with FMR and with thermal gradients, there's also been some really interesting work, is actually reopening the question of whether some of these fundamental limits can actually be approached. So we can, in other words, leave the additional off this and leave charge behind and really start thinking about pure spin operation. And that's pretty exciting. And one way that I would describe this is to say that it's a change in paradigm in the field of spintronics. Rather than mimicking the development pathway of charge-based electronics, to realize the fact that the presence of an exchange interaction, coupling between these two spins, sets a fundamental energy scale, sets up a resonance in both literal and figurative meanings of the word that we can exploit. And this may actually be a much easier place to look for spintronics. So I've been talking for a little bit, so this is a good chance to make sure everybody's awake. So I would be happy to go through my cartoon picture of FMR-driven spin pumping to motivate this in a little more technical detail, but only if people are interested in seeing that. So let's get a show of hands. Who wants to hear that? Okay, there we go. I won't ask the counterfactual then. So just to sort of give a little bit of a hand-waving explanation, at least my personal intuition for how this phenomenon behaves, you start off, and let's just ignore the right-hand side of this picture and consider the left-hand side, where we have a ferromagnet, and at equilibrium the magnetization is oriented along X. And then one of the great interesting things about working in spin and magnetism, in my opinion, is it's all angular momentum, so it's all cross products. So if I imagine what happens as I tip this magnetization away from equilibrium, it doesn't simply swing back like a pendulum, like a clock. It in fact precesses. And if I just give it one tip, it precesses in a spiral back to equilibrium, and as it does that, it basically experiences the magnetic version of friction. Right? There's some dissipation. Magnon-magnon scattering is a leading order. Everything eventually goes back to phonons, but you lose that initial energy in a precessional path. So, but the frequency at which it precesses is defined by the presence of an external magnetic field. So by varying that field, we can determine the frequency of this precession. So then we can ask the question, well, what if instead of kicking it once, I kick it periodically in resonance with its precession? So every time it hits a certain phase, I give it another kick. Then I can keep it going, right? Even though it wants to spiral back down to equilibrium, I'm putting in energy that's exactly matching the energy that's dissipating out due to the internal relaxation. So that delta function picture is not really the way it works. In a practical setup, it's a continuous oscillation in the gigahertz regime. So microwave fields with a circulating B field that is effectively pushing out continuously on this magnetization vector as it precesses, while there's dissipation pushing in, and at equilibrium, you come to some cone angle for the precession. Right? So it's sweeping out some cone. So the thing to point out is that none of these processes change the magnitude of the magnetization vector. Right? You've just tipped it away from equilibrium. But the magnitude of the projection along the z-axis has changed. Right? And so for an isolated film, that's internal dissipation. But the sort of exciting thing about spin pumping is that now if we consider the bilayer and you put a non-magnetic metal in contact with, say, a magnetic metal in the simplest case, then you see an additional dissipation term. So I've described FMR as a dynamic equilibrium where you're pumping in microwaves which are continuously pushing out, and there's some friction, some dissipation that's pushing in, and you come to some equilibrium. Well, all you do is effectively glue this to another metal layer, and now the dissipation gets stronger, which means this dynamic equilibrium shifts closer to relaxation. Right? So you go from this wider cone angle to a narrower cone angle in the presence of additional dissipation that magically somehow comes from the presence of this non-magnetic metal. And so this additional dissipation was discovered relatively early and then sort of set aside as don't do that. That makes the ferromagnetic resonance worse. But more recently what people discovered is this dissipation mechanism is a transfer of angular momentum from the dynamic magnetization of the ferromagnet, or from the magnons, if you will, to the free carriers in the non-magnetic metal. And so there's this net flow of spin with no net flow of charge. So you don't build up a voltage here, but somehow this pumping process is pushing spin across this interface. And this is sort of, when I was a PhD student, this was spoken of mostly hypothetically about a problem with spintronics. Spintronics is great, but there's no such thing as a spin battery. So we have to play all these games. This is, in fact, a spin battery. This is a way you can create sort of a motive force for pushing spins, but not pushing on the charge degree of freedom. So this is sort of all an introduction to the field in broad context about the state of play when we started looking at the results that I'm about to tell you about. So just briefly, Jan mentioned, or Sarah mentioned, some of our work in magnetic materials. As I've just described, we're also very interested in spin and magnetization dynamics, and based on work I did in my postdoc and subsequently, we're also interested in this sort of interesting nanoscale or mesoscale regime where physics changes due to the dimensionality, due to surface to volume ratio, et cetera. So my group covers lots of projects with various intersections of these three ideas. For the bulk of the talk, I'm just going to focus on this new materials development, and in particular, this material which I promised to get back to, vanadium TCNE. So again, I feel kind of funny presenting this work here because I'm sure a lot of you are very familiar with it in detail, based on this foundational work of Joel Miller's, who was a longtime collaborator of Art's. And also, I want to say this is the slide that I normally put up when I'm talking to physics departments without a significant organic spintronics component. So I think I should really use this title for this talk, because I'm sure you guys know about it. But the basic idea is you have these small molecules, these TCNE, which are shaped like an H, cyano groups at the terminus, and they're connecting between adjacent vanadium atoms. And the idea here is then you have either some super exchange or double exchange interaction where the vanadium starts off with 5 d electrons, gives up 2, that's sort of what's shown schematically in this diagram here, to charge the TCNEs to minus. And so that, in addition to the charge, that carries spin, that electron, so you have 1 spin pointed down, you have the remaining 3 vanadium spins pointed up. And so while this direct interaction is antiferromagnetic, the vanadium sublattice is ferromagnetically ordered, so this is called ferrimagnetic order. And if you add up all the spins here, you get a net spin of 1 Bohr magneton. So it basically acts pretty much like a ferromagnet. And
is that a unit cell of a crystalline material?
That's an excellent question. That's a unit cell of a hypothetical crystalline material. And one of the things about the evolution of this material over time is that it's certainly not fully crystalline. And initially solution synthesis and more recently CVD synthesis, the material quality continues to improve. And so one of the interesting things that's been happening in our work is a lot of the received wisdom we got from Art about, for example, the fact that this material must be totally disordered. may not quite be right. So I think actually there may be more of this happening than we had thought. And I have some data to explain why I think that might be true a little later in the talk.
I like to think of those as isolated.
Well, let's say it's continuous. The issue is that, and it's kind of hard to tell from this diagram, but not all of the TC&Es are connected to vanadium on all of their terminal groups. So that means some of them are free to rotate. So while, hypothetically, you can tile space with a crystalline VTC&E, practically speaking, this degree of freedom leads to disorder on some length scale. And that's something we're very interested in tracking down. We're trying to do some collaborations to do small angle neutron scattering to get a feeling for that length scale.
Is the direction of the spin orientation here related to the structure, or is it random?
Also a very good question. I'd say some of our recent data would argue yes, it is. This particular orientation is PowerPoint physics. That I don't know exactly the relation to the bonds, but I think we are seeing signs of some structural anisotropy. So I think this is one of the things that I was saying. We sort of assumed maybe not so much, but then as we're improving the material and doing more sophisticated measurements, we think there may be signs that is present.
Okay, sorry for the interruption.
No, great. And by the way, everybody feel free to interrupt because, I have plenty of slides. I can talk for as long as you guys want. I'd much rather focus on things that you're interested in. So as I mentioned a second ago, this is grown via CVD. So this is just a glass reactor. The temperature here is 50 C, so this is just sitting in a glove box. It's actually pretty simple to put together. The TC&E is its own precursor. For the vanadium, we use VCO6, and again, none of this synthesis is unique to us. What we have done is just worked to try and make this as reproducible and systematic as possible, and that's helped significantly. I want to point out, we just published a paper in this new journal, the Journal of Visualized Experiments, which I hadn't heard of until... Yeah. So until they contacted me, and initially I was like, no, that's okay. I don't need my 15 minutes of fame. But then something I've been talking about with some of the faculty over the course of the day today is, I think is kind of a weird thing to say at a colloquium, but this field is too small. I want more competition, right? I mean, we all like to be the first, and that's great, and we have some firsts to brag about. But if you're the first of one, nobody cares, right? That's less impressive. And so what we did was we took this is an opportunity to, as transparently as possible, push the synthesis methods that we're currently using out to the community. And anything that's not clear here, to be clear, this is a methods journal with a very detailed sort of prescription for how to synthesize it, and video of the process happening, and some of my graduate students, so it's their 15 minutes of fame. And if there's anything that's not there, we're happy to answer any questions about it. But so I see now 30 minutes of cartoons, which is a lot for a physics colloquium, so let me get to the data. So this is what I mean when I say it's actually quite a high quality material. So another joke I like to make with physics audiences who aren't used to this is that usually when I start a sentence and I use the words organic and magnet, I end the sentence with something that rhymes with dilution refrigerator, right? But that's not at all the case for this material. So this TC, take it with a grain of salt. We don't, for various reasons, it's tough to get a clean block law fit to this, but at 300 Kelvin, it still has 85% of its maximum magnetization, and sort of a linear extrapolation would give you an even higher temperature. But so whether it's 550 or 600 or whatever, it's very high ordering temperature. And the hysteresis at room temperature is quite nice. It's got sharp switching, a nice open loop. And this is taken from this paper here, so these numbers are references to prior work. And you can see moving from the powder synthesis to the thin film CVD synthesis. And then this is the work of one of my students who's just graduated and moved to Intel, Megan Harberts. And there's no magic sauce here, this is basically, as I said, just a matter of being as careful and systematic as possible in mapping out the phase space and the control for the growth. And we had sort of very nice properties in terms of sort of DC magnetization. And sort of this is the type of data, we're working with VTC of this material quality roughly, that inspired us to do the spin LED paper. And I'm really running low on time, so let me just jump to the results that we saw basically right as that spin LED paper that was coming out, that convinced us that not only is it a pretty good material, this may in fact be an excellent material that we want to pursue. So, and this is retroactively the motivation for that FMR spin pumping cartoon. So this is the ferromagnetic resonance spectra of VTC&E grown via this optimized synthesis process, and you can see it's incredibly sharp. So the line width of this scan is 1.4 Gauss. That 1 Gauss line width we can get fairly reproducibly. And the red and blue lines, which you can't really even see on this scale, are just the precursors, because the first thing we thought when we saw this was, wow, that's a really nice ESR spectrum. I wonder what's contaminating our sample. But then when we varied the angle of the DC field from in plane to out of plane, which is sort of a classic FMR measurement to measure the anisotropy due to the shape, you can see the line shifts exactly as anticipated. You get sort of a sinusoidal variation here. You can fit that using Cattell equation, extract the saturation magnetization to be sort of pretty closely consistent with what you get out of squid data. So this got us really excited, and I have to admit, even when we had this data in hand, it took me a while to figure out that this would be interesting. This wasn't actually the direction we were going with this measurement, but to explain this, I'm showing two plots here. So this is an older paper on VTC&E showing that even in films that show excellent DC magnetic properties, you have sort of more a forest of lines as you go from in plane to out of plane, and only at sort of very special angles do you get that nice narrow FMR line. In contrast here, we see this 1 Gauss line width pretty much over the entire spectrum. So this is to say, Megan's hard work does mean something in the end, more than just.
What is the difference? You're growing it more carefully?
Yeah.
What does that mean?
I mean, I'm not trying to be cagey. We didn't all of a sudden add a magic new solvent or anything like that.
I've done experiments like that too.
Yeah.
It works. I don't know why.
Well, it's not that. I mean, so I was going to include this slide and I forgot it. In fact, one of the things that we did to get to that point was we took. You can see here that it turns out the out-of-plane FMR spectra is the most sensitive to the presence of these extra peaks, and we basically we did improve the temperature stability and the feedback control of the CVD furnace we were using, and did careful temperature mapping of the thermocouple, so we knew if we put the sample here, it'll be this temperature. Here it'll be this temperature. So that's the kind of thing that I mean. But then we just mapped out all of the phase space that we could. The temperature of the VCO6 precursor, the temperature of the TC&E, the substrate temperature, the flow rates, and looked at basically, we have a plot of the FMR spectrum for all these different parameters, and then you sort of can make a phase diagram and say, okay, if you're operating in this regime of phase space, then you get the really nice FMR lines. The tricky thing is that so that's maybe 30% of the phase space. For 80 to 90% of the phase space, you get great DC magnetic properties. So it's the kind of thing that it's not that anybody missed anything big. It's just that, well, the first time we saw the narrow line, we did get lucky. And then we said, well, we want to be able to do that again, and we did this mapping, and we realized that essentially parameters needed to be more tightly controlled than they had been in the past. So the other half of this motivation, though, comes from this graph, which is a similar measurement on thin film yttrium iron garnet. So this is a workhorse material. So It's got a lot of recent excitement in the spin pumping field for driving spin currents into platinum and whatnot. But actually, when that kicked off, it was very hard to get sort of research grade YIG because it was essentially an industrial material, like sandpaper or something like that. I mean, people just mass producing YIG for use in microwave electronics. So even before Spintronics applications, people are very interested in this very sharp microwave resonance to do sort of very careful spectral filtering and phase shifting of microwave signals and stuff like that. And in fact, it's been well known in that community for decades that YIG is this magic material. That YIG gives you a line width of about a Gauss, and everything else is 10 Gauss or higher. And people have spent actually a fair amount of time on combinatorial materials trying to come up with other versions of YIG so that they can get some tunability and other options with limited success. But I think, as much by luck as by intelligence, we've stumbled across a material that in fact does all of that. So we're very excited about it. So now here's how the second slide that I had to modify. So given these great properties, why has VTC&E not taken over the world, right? Why am I standing here arguing that more people need to get into this? I suspect that people here know, so again, modifying the slide a bit. As I said a few minutes ago, VTC&E is very air sensitive. It doesn't have much or any in-plane anisotropy, coming back to this issue of structural ordering, which is okay for some applications, but others you really would like to have that degree of freedom. And not that it's intrinsically impossible, but there had been relatively little work done on integrating VTC&E with other materials to make functional structures and devices to take advantage of this. So basically, building off this result, we said, okay, we think this is a really exciting material. We want to double down and move forward with it. And over the past 2 to 3, well, that's longer than I thought, 4 years, 4 to 5 years, we've come up with a series of sort of technical breakthroughs that we think will really allow this material to move forward in new and exciting ways. So one of the more important technical aspects is addressing the air stability. So using encapsulation techniques developed for OLEDs and OPV, we can extend the lifetime of VTC&E films under ambient conditions from 30 minutes to almost a month. We've been playing around with modifying the TC&E ligand. I know we're not the first to this train. We can actually do a fair amount of modification as long as all you want to do is make the magnetic properties worse. So that's unfortunate. It would be great if we got like a 900 Kelvin Curie temperature or something like that. But in all seriousness, some of these modifications generate new magnets with lower TC, but lower than 600. So for example, we have a variant METCEC that still has a 300 Kelvin ordering temperature, which I believe makes it the second organic-based magnet to be magnetically ordered at room temperature. So this allows us to start making heterostructures, all organic or all organic-based magnetic heterostructures, which is pretty exciting. And then very recently, so this is all published work that I'll put up the references at the end of the talk, but very recently we've also discovered these new morphologies. So for example, when we grow on SiO2 substrates that have been nanopatterned to have these ridges, rather than getting a conformal folded sheet, we actually get these nanowires. And so this makes for great SEM images. Beyond that, it turns out that these structures introduce exactly the in-plane magnetic anisotropy that we've been looking for. So I spent more time than I had thought I would in getting us to this point. So maybe I'll have another alertness check and take another audience vote. So I have plenty of slides about all of this stuff that I can talk about in more detail, and I have maybe 10 minutes left. Or I can show some unpublished data on stuff that we don't understand at all. So who would like to see the published data?
Can I make another suggestion?
Yeah.
Could you explain why this is actually a ferromagnet, not like anti-ferromagnet?
It's a ferrimagnet.
Oh, it's okay, ferromagnet.
Well,
Why not?
well, that's the point. A ferrimagnet is an antiferromagnet. It's an antiferromagnet where one of the two spin subsystems is bigger than the other, so you end up with some net moment without perfect cancellation.
So this has nothing to do between which orbitals electrons hop, you know, within these vanadiums and whatever the
No.
group is.
No. So yeah, so like classically, the majority of all magnetic ordering is antiferromagnetic, is what I think you're probably referring to. And so to get ferromagnetic ordering, usually you have to hit some magic sort of set of circumstances with bond angle or orbitals or something like that to generate ferromagnetic ordering.
But the transition metal of ferromagnetic. The ferrite between the metal and the ligand. The antiferrite.
Yes, yeah, and that's generically true for a ferrimagnet, yeah. So, but it's, well, I mean, so this is common terminology in magnetism, and you can argue that it's a little bit, argue the semantics of it. But I would say, so the ordering between the vanadium sublattice is ferromagnetic in the sense that they're all pointing in the same direction. It's not ferromagnetic in the sense that there's a direct exchange interaction. There's a negative J between the vanadiums. All the J's are positive, giving us antiferromagnetic order. But like I said, rather than having an alternating sublattice of identical spins, which would leave us with no net magnetization, one of our sublattices has a stronger spin than the other. So we're left with an excess. And that excess spin then provides effectively a lever arm that we can grab with a magnetic field, and it behaves pretty much like a ferromagnet.
Great, thanks.
Mm-hmm. So that was a quick one. So we still have about 10 minutes for Plan B. So unexplained, unpublished data. Okay, that's a popular choice. Okay. So where should I go? So let me just quickly introduce this. So I mentioned that we have different ligands, and Art trained me well enough to pronounce tetracyanoethylene, but not these. So these will be known by their acronyms of METCEC and ETCEC. Still not enough of a chemist to do that. But you'll notice there's increasing sterics on this axis and also increasing electronegativity, which affect the magnetization. And I just want to, and all three of these are complexed with vanadium, giving us three different versions of ferromagnets. Here we go. And the data I skipped over proved what I just said. But if you take my word for it, and I didn't realize these lines were so narrow. So what I'm showing here now is this vanadium METCEC that we've developed. And what we're doing is we're rotating the angle from in plane to out of plane, in plane to out of plane of a thin film of this material. Right? So it's the same measurement that I showed you for the TCNE where we saw the magnetic resonance shift. And the interesting thing here is this is two different temperatures, which I left off the label. So I promised, unpublished, ununderstood, and poorly labeled. I should have, oh no, here it is. So this is 140 Kelvin, and this is 80 Kelvin. And it's kind of hard to see with the naked eye without putting a line on the page, but in fact, these peaks go in different directions. So that's pretty weird. You can see that more easily here, where I'm just showing the central peak as a function of angle. And you see the same kind of sinusoidal shape that we showed for VTC&E, but the phase flips. So this is really interesting and quite surprising. And so what this means is that the easy axis,
The temperature of measurement or the temperature at which you...
temperature of measurement. So as a function of temperature in these films,
Same film.
same film, exact same sample. So basically the easy axis has gone from in plane to out of plane. And so this is one of the pieces of data I was referring to that makes us think that maybe there's more structural order than we thought. And I think to explain this, I need to jump back to another slide that I skipped over. Let's look here. And think about the mechanism of the magnetism here. So at low temperature, and here I've sort of cartoonishly indicated regions of high structural order or grains of high structural order with intermediate blocking regions that are disordered. So at low temperature, you have some local magnetic ordering. Think of it maybe as super paramagnetic ordering. But grain to grain, that ordering is not well defined. And this low temperature phase means below about 150 Kelvin. You can see the magnetization's dropping. So this behavior, and if we apply a magnetic field, we can recover this. It's sort of like a spin glass, but it's not really a spin glass. There have been theory papers referring to this as sparimagnetic order, which is yet another exotic magnetic ordering. Although I've had people in similar talks claim that sparimagnetic ordering means something else. I don't have a dog in that hunt. I'm fine calling it. It's weird. But what we think is happening is that this is also a reasonably good organic semiconductor. So mobility is maybe somewhere between 0.1 and 1, I think, for typical films. So as we heat it up, we start thermally activating more and more carriers. And as those carriers can move around over larger distances, they can bridge some of these gaps and drive global uniform magnetic ordering in the film. So this is what you're seeing here, this rise. As you go from low temperature to high temperature, it gets better ordered, which is weird. What's that?
Just a little bit.
Well, that's because these are optimized films. So, for example, I can show you for the METC EC, this is a much more dramatic effect as we make the film more disordered. And so this is pretty weird, right? Most ferromagnets get worse as you make them hotter. But not only does the magnetization increase, but that hysteresis loop I showed you at 300K, which is nice and sharp, gets very squishy and sort of banana-like as you go to low temperature.
What's the ordering mechanism when there's few electrons?
We think it's very local. It's this local super exchange or double exchange mechanism, but it's only happening within one or two lattice sites. And that maybe one way to think of this is, and again, there's a lot of unknowns here, so I could be totally wrong, but this is the way that we think about it. You know, if you imagine each of these locally ordered clusters as a hopping site, and hopping between these turns on as you go to high temperature.
What's hopping?
Electrons. Oh, yeah, carriers. I won't even go that far. Carriers. Yeah, and I think I should say there's some evidence that it's ambipolar. But yeah, so, but coming back to the FMR data, then what I think is happening is that at high temperature, we have a globally ordered film. That means the magnetization everywhere is pointed in the same direction. That means we have significant demagnetizing fields. And we have classic thin film anisotropy that you would see in iron or cobalt or something like that. But as it gets colder, the film is no longer globally ordered. It breaks up into these individual domains with local magnetic anisotropy, which effectively looks like a ferromagnet that's been demagnetized. Right, and the demagnetizing happens, so it has lots of domains, right? So then the demagnetizing field globally gets much weaker. So it's just not important. It's not contributing much energy to the system. So then but we still have anisotropy. So this is what I think our leading explanation for this is that there is actually some residual structural order, maybe even just templated off the hard surface of the substrate that's producing some real magnetocrystalline anisotropy in the material.
What is the substrate?
It's sapphire for these samples so that it's happy in the EPR cavity. Although, yeah, that's a whole other interesting topic of discussion. So maybe I'll just put up one or two more slides because we're almost out of time. So here's some pictures of nanowires. Lots of fun. This is what the in-plane anisotropy looks like. So just to show you that we can do that. And I think maybe the last thing I'll show you, and this is very poorly understood, is rather than depositing on sapphire, we can deposit on YIG. And then in principle, we've made a bilayer of the two narrowest line width sort of best ferromagnets that we can. For reasons of attempted cleverness by the advisor, this is VETCEC rather than VTC&E, which didn't end up working out. But the thing I want to point out is here, this material is maybe not of the highest quality. So this is the line corresponding to the organic, and this is the YIG line, which is tuning through as we vary the angle. And so basically we can use the shape anisotropy and magnetocrystalline anisotropy of the YIG to tune its resonance frequency through the resonance frequency of the organic. So out here they're decoupled, but as they get closer, these resonance frequencies start to line up, and we think, you'll notice that the organic, multi-lined organic response collapses into a single line that's significantly narrower than the YIG
This is actually
far away.
interaction and changing the way that the subsystem behaves. It isn't just like two lines that pass through each other.
Exactly. So they're not just spectrally tuning through. We think there's strong evidence of interaction and coupling, which could be and we need to do more work before we can say this conclusively. But this could be evidence of exchange coupling between the organic-based magnet and the inorganic-based magnet, which would be very exciting. I don't know of another case where that's been demonstrated. And then ultimately, we'd like to come back to the beginning of my talk and actually do spin pumping experiments. But
What's the thickness of your layer compared to the distance between centers of magnetism?
well, so the YIG layer in this sample I think was 20 nanometers, and the VTC&E it's tough to get an exact measure, but say 50 nanometers or something like that.
How far? Okay, and your vanadium centers are.
Oh, angstrom, yeah, just a few carbon atoms apart. So very, very thick. It's a bulk. It's a bulk material, bulk film. So maybe I should close there and just say that, in summary, we're very excited about the future for organic-based magnets. We think they're exhibiting some new properties that we hadn't realized when we started this, and through sort of various technical tricks with encapsulation and careful synthesis, we think, it's still not going to work at 300 Celsius. It's still an organic material, but reasonably robust, where we can start to think about applications of this. And so maybe I will just say that we think there's a bright future, and anyone interested in copying down the references for the stuff that I didn't say, I'll put those up there, and thank you for your time.
Here comes the 64,000 question.
Okay.
Have you achieved spin pumping with your organic ferromagnet?
No. We're working very hard on that. But yeah, I don't think we have evidence of that.
And what's the problem there?
That's a good question.
Have you done an experiment? What
well, so-
you see? Just no damping, or
I'm not. So just a simple damped, not damped. I'm not convinced that that's a great measurement because. So for example, putting it on top of a high spin orbit material versus a low spin orbit material. I mean, there's enough questions about how the material grows that even if the line width changes, I wouldn't be convinced for our material at least that that's. But what we were trying. So we have another version of this sample that has an aluminum layer between the organic and the YIG. And so there's some very nice FMR work by Brett Heinrich and collaborators where they do an all FMR detection of spin pumping by seeing similar line width narrowing as they come into resonance. So here there's no interlayer So it's more an evidence of exchange locking, I guess I should say. And well, I'll say for this technique, the problem is this. And so the clever thing I thought I was trying to do with using the VETCEC is the low Curie temperature means we can measure above and below the Curie temperature. So we actually have done this with VTC&E as well, but we didn't have, it's not easy to turn it off. We didn't have like a good control measurement. So here we were thinking, oh, we can vary the temperature. And what we failed to take into account, these black dots here are the line width as a function of angle for just bare YIG. And it's actually quite complicated line shape. And so that's sort of slowed us down a little bit, that there's response in the YIG that makes it not so easy to interpret the line width. We're working on it, and we think that we may be able to, but we haven't been able to yet. The other thing to try is, say, growing it directly on platinum and looking for some sort of inverse spin Hall signal. And there, we still could try that. I think the reason I was leaning towards this is, and we've done spin pumping measurements in inorganic systems, and as I'm sure you guys appreciate very well, there are a lot of potential transport artifacts in that measurement. And so I was, famous last words, I was thinking this would be easier, at least, or less ambiguous. But none of what I'm saying is definitive. This is why it's not yet published. We're sort of in process. But I have high hopes that we'll get there. I mean, it's just a matter of turning the crank enough times until we get the right set of conditions.
What's special about vanadium?
It's not clear. So there's been a lot of prior work in this area with replacing the vanadium with other transition metal atoms, and they're all almost all magnetic with lower Curie temperature.
Something that wasn't going to be.
Yeah. My guess, and this could be my own prejudice showing, because I did a lot of work with gallium manganese arsenide as a PhD student, but my guess is that it's this high temperature stabilization of the magnetization, and you want exactly 5d electrons to make that go. I can't prove that, but that's my best guess about what's special about vanadium for this system.
When you say that this order somehow is stabilized by this new carriers introduced by temperature, you don't mean any kind of RKKY stuff. You mean something different, right?
I don't know. It's RKKY-ish. I mean, RKKY assumes band carriers that are oscillating with like some very well, and these are hopping carriers, right? So they can't be doing exactly that.
You're just saying that somehow the energy of these hopping carriers gets reduced enough by uniform magnetization in order for that magnetization to get uniform.
Yeah, that's the one way to say it.
Exactly, that's done.
Yeah, or another way to say it is just if you look at the typical length scale, the average length scale for a carrier in this hopping regime is temperature dependent. And as that length scale gets to be large on the scale of this inhomogeneity in the magnetization, it helps to anneal it out.
Was it ever seen in some other, like in this gumnas that you mentioned? Something like that?
No, but that material was in a different regime for carriers. So famously with gallium manganese arsenide, the manganese is also a dopant. And so you're introducing a dopant to gallium arsenide at alloy levels. So the carrier, it's still a dirty metal. It's still not a great conductor, but there's 10 to the 20th carriers or something like that. So I don't know that you would see that effect here.
What are the chances of crystallizing this stuff?
Not
Hard
not
enough to do
not
with
bad. That's not my expertise, but I think it's plausible. So one of the things we're looking at is, I totally skipped over the nanowire stuff, but you could imagine, if I were to push hard for that, I might try templating the substrate at some very small length scale. This has been successful with other organic materials, like rubbed substrates for copper phthalocyanine, I think, if I'm remembering correctly. I may have the material wrong, but basically, yeah, that through templating effects you can sometimes get crystallization, but I'm sure there are synthetic chemists out there with more talent than I have that could come up with
Lots
it.
of room for growth there.
Yeah. Yeah, which is sort of coming to the theme I started with. There's not enough people in this field. Like, it's strange because in other areas of research that I'm working on, we sort of want to be cagey with the preliminary results because we don't want someone to beat us to the punch. But I can only afford 2 graduate students on this project, and there's easily 8 graduate students worth of work just based on this talk. So I'm perfectly happy to collaborate, share information, just get more people working on this. I think that'll help out the whole field move forward much more rapidly.
Any more questions? Okay, let's have the speakers.
Yes, some. Yeah, so there's a strong resistance effect. It's the linear negative resistance, which is another one thing about this material. So it's absolutely negative. But yeah, this is a yeah, that's something we're really interested in. In fact, the nanowire structures which I flashed out, that's the system we're most interested in transport. Because that has a really well-defined anisotropy and preferred direction for ionization, and then looking at how that interacts with the transport. Yes. I'm trying to think whether we did that. I assume so. I just can't. It's like a. No, I mean, it's not large for spin valve. It's a few percent per Tesla, which I don't know. Just look for that. If you start doing spin valve, multiple spin valve get which one.
It's a good place. It's the first in Salt Lake City to identify itself as 15th and 15th. Now there's 21st, 21st. Oh, you know, everybody's going to want to have it. Art galleries, trade store.
Yeah, it's like. Except for I think it's not. I think it has the same sign actually. It's just like a spin valve.
Oh, it's right next to Masa.
So if you think about how a spin valve behaves, it's happier if the magnets are aligned.
Yeah. Yeah. So I would like to go as quickly as possible. Yeah. We can see people now. But
That's at least in a general sense, I think.
yeah.
Maybe
Yeah, I don't. So I don't want to
Yes.
dictate the schedule, but if you ask me, then
I don't have
Yeah, in principle.
Okay.
I mean, we've
Yeah,
got the
then I would
temperature
just
cycle
that's
checked.
what I
It looked okay. We haven't looked at it.
whenever
In a lot of
everyone's
detail.
ready, I mean, go right away.
It's black.
Okay, are you going to take it?
Yes.
Yeah, okay, great.
The optical properties
Okay,
have
then we just have to
sure
figure out
been
the time.
that thoroughly explored. The main work that I can think of is Art did an experiment illuminating AE and getting a cis-trans rotation in TCE magnet, which strongly suppress.
No, I was trying to call earlier, but the open expired.
Oh, okay. Well, let's just go there.
It's not for arresting.
No, but